let's say this, you have 4 wines. So we want to talk about the area of this vector, the vector area of the coil. So the vector area of the coil is this one of these circles here. All right, then it could be.
Good evening, everyone.
Okay, Dale is here. Welcome, Dale. It could be that of this other one. It could be this for this other one. Okay, but the vector area of the coil is one of these circles, which is inside here. All right. I would want you guys to read a bit more about torque, because it's usually generated by the interaction of the dipole with the magnetic field. So your torque would be your M times your B, and B is the magnetic field vector. And I've noted it for a spacecraft, it implies the Earth magnetic vector. All right, these values may be given to you, otherwise you may have to identify it yourself. Your M will be computed from this equation. All right, and then your torque will be computed multiplying M by B. I would want someone to tell me, why is it not this? And you tell me the difference between this. What's the difference between this and what we have here? What's the difference between these two equations? I'm waiting. What is the difference between those two equations? Okay. So which one is orthogonal? Yes, that's correct. So the cross is orthogonal. So what this tells me is, let me just clean it up. Eraser, where's the eraser? So what this equation tells me is that M is perpendicular or orthogonal to B. All right, and that's why we're using the cross multiplication, and that will help us to generate a resultant force. Now let's think. Suppose that your spacecraft is going in this direction, and then that's I'll draw it. Suppose your spacecraft is going in this direction, and there's a magnetic force or field in this direction. That tells you there's going to be a resultant force, right? And this resultant force is actually going to tell on your spacecraft. Do you agree? Do you agree? Okay, I'll say it again. Suppose there's a magnetic field in this space, and that is what we, for instance, the Van der Age. Remember this, which generates magnetic field, and then your spacecraft is also in this direction. Now there's definitely going to be, remember, it's going it's revolving around the Earth. It's revolving around the Earth, and then there's your heart revolves in a certain direction, let's say this direction, and that's how your spacecraft is revolving, and you're sending that into space. and then there's another magnetic dipole here. Definitely there's going to be a resultant force between these two, and that resultant force would have an effect on your spacecraft. So what we're saying is it's the magnetic field which exists in space would actually have effect on your ADCS. So we can use that to an advantage as an engineer. So what we can do is we can generate an internal magnetic field in our spacecraft, which can be used to align the altitude of the spacecraft with the magnetic field outside this magnetic field. So you see, I cannot expand this, but the red circle, which is this is your heart. You can use this internal magnetic field to place or to align the altitude, so to create a path for your spacecraft. That's simply what I mean here. You have two magnets, right? If you put them together close to each other, they repel each other, pushes it apart. But when you have, you can actually use that to create a path around. So you can put a magnet in your spacecraft, then use that to create, align the altitude of your spacecraft with that other magnetic field. So here to create a resultant force in the direction which you want. So basically you can use this to control your altitude. And there's another thing we call 3 degrees of freedom. Does anyone know about that? Okay. Oh, the three of you. All right. You can, it's easy to see. You can Google and see what that means. But basically what you can use this for is you can use it as to your own advantage as an engineer. It has effect on your ADCS, your control subsystem, but once you do your torque computation or calculation, then you can use it to align your spacecraft, the altitude of your spacecraft. That's basically what I mean here. But what is important is you need to be able to do your torque computation. It's a roll, pitch, and yaw. Basically, it's your orbit. That's what I mean. If all of the three you have said means your orbit, then it's fine. Okay. Any question before we go on? I need you guys to understand all of this I've said. Um, okay, thank you. So we're also going to see another effect of the magnetic field. Your magnetic field can also affect command and data handling subsystem. Okay, and how does this happen? Your magnetic field will influence particle motions in the Earth's orbit. Remember, your particles are charged particles. So it may pull, and that is actually answering why you have that 5,000 kilometer distance apart between the inner and the outer Val-Allen radiation belts. Okay, because of the, remember, it's caused that belt, those belts are caused by a magnetic field effect. So when you have the two close to each other, it's going to repel. So there's more like a repulsion between the two. Okay, I've actually answered that question, but you can still think about it and make sure you watch the video. So this will always influence the particle motions. And how would this happen? If you have a particle, if you have negative charge particles, they always want to tend towards positive charge particles. The same thing applies to your positive. They want to tend to your negative charge particles. So that's really happens as a result of your magnetic field. And if you have a command and data handling subsystem, then you need to take care of that effect. And also it deflects some particles from interplanetary space. So it's the same effect. They get attracted to the opposite charge. All right. And yeah, that basically will affect your command and data handling subsystem in your spacecraft. Now let's see the effect of atmospheric pressure and temperature. Obvious, this we call thermal effects. And let's look at this critically. Back to this diagram. We're starting from our troposphere. I'm looking at this diagram now here. We start from troposphere. Look at the temperature we're starting. This is where you have Mount Kilimanjaro, Mount Everest rather, not Kilimanjaro. Mount Everest is 8.85 kilometers, right? And it's somewhere between in your tropopause. The tropopause is the line between your troposphere and your stratosphere. So if you climb up this Mount Everest, you starting from here, you have your temperature decrease. And that's why when we say we're going up mountain, oh, it's getting cold. When you get to a certain level or a certain altitude, say you get to your 10 kilometers or the top of Mount Everest, you see that the temperature is around negative 55 degrees. Okay, now you passing through your tropopause, you get into stratosphere, you see what happens to your temperature. It increases again until you get to your stratopause. You get to stratopause, your temperature at stratopause is negative 10 degrees. In between, I mean, in your stratosphere, that's where you have your ozone layer that protects the Earth from all of the radiation from the sun. And now you're here at 50 kilometers height. You have temperature increased from negative 55 to negative 10 degrees. As you climb up again, you're sending your spacecraft into the space. It goes again into your mesosphere. Look at how temperature decreases. And here you have it at around negative 80 degrees at your mesopause. That's like 85, yeah, 85 kilometers high. Now we're getting into the thermosphere. And here in the thermosphere, where some engineers say it's the space, but I would say exosphere is the space. You see how your temperature increases. And here it has actually increased to like 20 degrees. The moment you're now going away into your exosphere, your temperature continues to increase suddenly like this. Then you can think about the effect that we have, all of these temperature changes will have on your spacecraft. Okay, so it's actually something that engineers should think about when they're doing space rocket launching or when you're going for space mission. All right, and the same thing happens, or let's consider what happens with pressure. At the top of Mount Everest, your pressure decreases to about 250 millibars, and then you get into your stratosphere, your pressure decreases to zero, and then you continue up, 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 up until you get into the space where you don't even have anything. And this also will have effect on your spacecraft. So I've put something right here as something that we can reason about. With the thermosphere being very hot, relatively, and the exosphere being very cold. So the moment you get out from the thermosphere into the exosphere, it becomes very cold. And that is a sharp or a sudden. Oh, I've actually answered. Answer that. I wanted to ask you guys, that change, is it going to be gradual or sudden? But it's actually sudden, very sharp change with respect to your altitude. Now, how does spacecraft deal with this change? It's something we need to think about. Can someone help me? Can someone tell me? Think about it. How does spacecraft deal with this sudden change in temperature? It's still fine if you're coming from troposphere to stratosphere, you can see the curve and all of those changes. But from here, it can be like this.
Okay,
So
so
how are you going
usually,
to deal with this as a spacecraft engineer?
so usually a spacecraft, they have a built-in power system which uses solar panels. Um, but besides that, there's usually lithium ion batteries, so that um,
I'm waiting.
keeps charging while the
Del,
sun is.
Del, sorry, Del, I can only worry.
Ikon chị
Oh,
she
can
have
you hear
to
me?
answer in the chat.
Okay.
Oh, you can hear me.
Is anyone answering the question? If you know, please, you can just type. Dale, I'm having issue with hearing what you guys
Oh, should I?
says. So you can just type in your answer in the comment section. Temba, Nita, Ibrahim, Dale. How will you, as an engineer, how will you deal with that? I'll wait for Temba to finish typing. Hello, is anyone still there? Can say hear me, guys? Okay. Should I leave that as an assignment for you guys? Okay, I'll read out Timber and then Dale's response to this. Timber says, yeah, the spacecraft is designed with components that can stand against severe temperature or layer protection. That's correct. Spacecrafts are always basically you have insulation. This will help you to minimize the transfer of heat between outside and inside of the spacecraft. Yes, that's right. And then you also have thermal control system, like what I think that's what Dale is trying to say. So usually a spacecraft has a power subsystem. Okay. Yes, you guys are brilliant. Yeah, okay. You guys are brilliant. Yeah. So Dale is like this power system is made up of lithium-ion battery and is connected to solar panels. They get this from the sun. Each spacecraft has built-in temperature sensors for various points in the satellite, and this is controlled by the OBC. There are built-in heaters. Okay, yeah, that's what Nita has said. Conduction, induction, conduction and radiation rather. Um, this is controlled by the OBC. Temperature changes, the signal gets sent to the OBC and tells the system to power on the heaters. That corrects the change in temperature. Okay. The thermal system in the spacecraft is used to stabilize. Yes, that's correct. Therefore, before the entry of the exosphere, the heaters can be used to compensate for the sudden drop in temperature. Yeah, same thing like what Dale said. Convection, conduction, and radiation. Yeah, that's also correct. Like having a cooling system that runs fluids, etc. Perfect. We're still going to talk about convection, conduction, and radiation. So I am going to save that. Thank you. Those are perfect and beautiful answers. Now, another effects of atmosphere. There's something we call the atmospheric drag. And this would always have an effect on your ADCS and your mission architecture. I think this, oh no, it cannot be done here. There's a slide actually, there's something which I would want you guys to see, this atmospheric drag. I'm gonna quickly share something which I want you guys to see. Okay, I can do it here. I'm trying to open up something for you guys to see. Okay. That's regarding atmospheric drag. All right. Permit me to share my screen again. I want to share my screen. Can you all see this? Mm. Could you see this orbital lifetime, this site? Okay, I'm gonna put it back because I want to be sure everyone. Okay, now this is where I got the diagram from, and here you can actually see what it's meant by that. If I click here, will you be able to see it on this slide? Okay, it's fine. So I'm interested in something on this slide, on this page, and that's why I actually put it here. Let's see, in the introduction, it says all satellites in Earth orbit are subject to various perturbing influences, which can alter their orbits. Satellites in low, that's LEO, with perigee altitudes below 2,000 kilometers are predominantly subject to atmospheric drag. Okay, and it implies that this force very slowly tends to circularize and reduce the altitude of the orbit. And it says the rate of decay of the orbit becomes very rapid at altitude less than 200 kilometers. And by the time the satellite is down to 180 kilometers, it will only have a few hours to live before it makes a fair re-entry down to the Earth. The temperatures attained during this re-entry are usually great enough to vaporize most of the satellite, but if it is particularly large or under certain conditions, component pieces may reach the ground. This is just about your re-entry into the Earth, and it's very nice to know that yes, there could be a kind of effect of sending your satellite into space, but also we need not to completely bother, because at some point you have them vaporize. At some point the speed reduces before getting into the Earth, and that is due to this drag force. All right, so before your satellite re-enters into the Earth, there's this drag force in the atmosphere that actually acts on it, that reduces the speed. That is why I'm interested in this document. And you can actually calculate this drag force with that equation. Let me go back to my slide now. You all have the link. Oh, okay, yeah. You all can go through, click on the yellow. Okay, it's there. Click on the link that is there. You can always get to that document and read more about it. All right, we're back to our slide. So you can actually calculate the drag force using this formula. Suppose this is your space object, that is your satellite. There's this drag force on it, and that's the velocity which is perpendicular to the cross-section area. So you can use all of these formulas. There's a lot you can read about uh, atmospheric drag, but it's has an effect on your ADCS and mission architecture. So you can actually compute this drag force to know um, to get an estimate of your re-entry of your satellite re-entry into the Earth. Okay. When you click on that atmospheric drag, the underlined one, it takes you to the link. And same thing again with your atmosphere in re-entry. You also have effect on thermal emission architecture. And here I have this question. Which region does the CubeSats burn up after their mission ends? Where do they burn up? Is it in the mesosphere area or in the in which area? It's Nita says in the atmosphere. Okay, in the stratosphere. Any other question? Any other one? Okay. So why do you guys say it spawns up in the stratosphere? Can you guys click on, I don't want to leave this slide. Can you click on the re-entry? It should take you to like we had in the other case. Okay. Are you all there on that? Are you all there on that spaceacademy.net? Okay. Can you go where you have the re-entry process, where you see the same diagram? Are you there? Okay. Okay. So let's now read that together. It says the re-entry process. Uncontrolled re-entries are always at very low grazing angles, less than 1 degree. The re-entry object is traveling at about 8 kilometers per second down to below 8 kilometer altitude. Break up, that's the question I ask now. Break up starts at around 78 kilometer altitude. And what is 78 kilometer altitude? That's above your, that's in your mesosphere layer, let's say, close to your thermosphere. Okay, so it's not your stratosphere. And this is termed the re-entry interface. Time from breakup to impact is from 6 to 30 minutes. The length of the re-entry footprint mostly depends on the re-entry process above 50 kilometer altitude. The width is also affected by tropospheric winds. All right. So I just want you guys to be clear that your breakup process or burn up would actually start after your mesosphere or in that layer. Okay. You can, I would recommend that you read up this article further. Now we're here in the vacuum layer. I've said at the beginning of the class that your space is actually equivalent to your vacuum. All right. And this also has effect. And what effect does it have? It has a thermal effect. Remember that your vacuum or your space or your what's it called now? Your exosphere, it's very cold. And we have actually spoken about that effect changing, rapid change from your thermosphere to your exosphere. And like Nita mentioned, the way we control that change, it's actually within, you have interaction from within your spacecraft and the external, that's the space, and then you also have an internal control system. So basically in space, since you don't have conduction of heat through here, then your spacecraft are insulated to manage heat transfer through other mechanisms. Like you guys have mentioned, you have two important mechanisms. One is the radiation heat transfer, the other one is conduction. Your radiation heat transfer, it depends basically on your electromagnetic waves, and is the dominant form of heat transfer between your spacecraft and the surrounding, that is the vacuum. And not only the vacuum, all of the surroundings in space or the space environment. And it uses thermal radiation, specifically. Then inside of the spacecraft itself, it uses conduction as a form of heat transfer. Okay. Just this to think about. If there is no conduction or convection and only radiation is present in your vacuum, how can this pose a significant problem for spacecraft? I'm just thinking out loud. Suppose you don't have conduction or convection and you've only got radiation in your vacuum. What's the problem that can cause to your spacecraft? Anyone thinking about this? All of those things highlighted in blue, they're just my thinking out loud, like thought, reflection, and things to discuss. What's going to happen in your spacecraft if there is no conduction or convection? Anyone thinking? Don't think too far. Just think about. Yes, this is generic, Ibrahim. Yes, it's right, but it's too generic. It's too broad. Just think about yourself in a spacecraft, and there is no conduction, and then there's no other way of heat transfer. What's going to happen? Yes, yes, that's very correct. You have it affecting your electronics. You have it affecting your control system. That is absolute correct. So yeah, we're almost at the end of our slide. We have high energy radiation and plasma. One of you should prepare a slide and try to talk about plasma. I don't know who the person will be, but I'm sure one of you in your slide, in your task, you should tell us about plasma. Okay. And we have high energy radiation and plasma in space. Um, for instance, these three are major radiation sources: trap radiation belts, which we have spoken about, galactic cosmic rays, and solar flares from the sun. Okay, these are major radiation sources that actually would affect our CDH. And the table shows you the particle types. You have electrons and protons from trap radiation belts. That's with your VA belts. You have high energy charged particles from your galactic cosmic rays that radiates directly towards the Earth. But you have your exosphere, you have your thermosphere that protects the Earth. Then you have the solar flare that comes also from the sun, with particles such as electrons, protons, and your low energy heavy charged particles. Of course, these are also protected by your exosphere, by your thermosphere, and all the layers protecting in the atmosphere, protecting the heart. The only one that is close to the heart is your um, VA belts. Okay. And what are the primary effects in devices? Remember, I said this will be affecting your CDH. You have effects such as ionization damage. You have your sensitive devices. The SEEs will be ionized actually. You have attractions. You have opposite charges attracting each other. You have similar charges repelling each other, and all of that. That's going to affect your devices, and so on. Ionization basically is a major problem when you have high energy radiation and plasma. Okay. On to the next slide. Your plasma. Again, this morning I actually was trying to describe plasma to my 8-year-old daughter. I'm sure all of you knows you know what plasma is. I try to describe it to her using the concept of lava. Okay, she's so used to that. So it's the floor is lava, the floor is lava, and then they play those games. So I'm like, your lava comes out from volcano eruption. It comes out in forms of liquids, and of course, we know there in our basic elementary science, they tell us there are three states of matter. It's the solid, it's the liquid, and it's the gas. However, there is the plasma as the fourth state of matter when you go into space. So I said you have the eruption from volcano. It's in form of liquid. Let me use that word, liquid, and then it's later solidified, becomes a rock. Similar thing with your plasma. It's going to affect the orbit and electrical paths of systems, your EPS. That's because they are extremely hot particles and they can actually hit the spacecraft. And if that happens, severely affects your spacecraft, the orbit, and your electrical power system. There's one important one basic or major one, which is called the sustain axe. This sustain axe, it actually develops if the plasma hits the spacecraft. There's the initial arc that we are called due to spacecraft charging. Remember, your spacecraft also has some electromagnetic charge. In this case, it's charging at greater than 100 volts. And then your plasma is also charged, it's also a charged particle. And then it hits your spacecraft, then it's going to actually cause an initial arc. Then this arc plasma, it reaches solar array strings or other surfaces at this voltage greater than they're about 50 volts. Okay, the initial arcs will now evolve into a sustained arc. Okay, and that will happen between spacecraft high voltage components. Then this arc continues. So far, you have current and voltage supply. Okay, remember that's your plasma, and then this arc melts, and then it completely destroys your system. Just think about that huge effect on your electrical power subsystems in your spacecraft. So that's a major one, and I would like anyone who's telling us about plasma to just try to tell us a bit more. So there's this force which we call the Lorentz force. You can someone please click on this red Lorentz force and see if it takes you to that article. Let me know, does it take you to the article? It should. Oh yeah, it should. It will take you to the article. Okay. So you can actually, yes, thank you all. So you can actually read about this Lorentz force, and that's if your spacecraft generates an electrostatic charge on its surface in the planetary magnetic field, uh, it will actually be subjective to this Lorentz force. Okay.